Knowing how to architect a recording pipeline for robotic data is quite a big deal because we don't want to just store everything in one big ROS-back file, which is hard to manipulate and maintain. What we really want instead is a simple setup which is robust and easy to scale. So in this video, we will set up a recording pipeline which follows all of the best practices, such as separating file by either time or file size, automatically removing all the file to make sure we don't run out of space on the robots, using chunk level compression instead of wall size compression, streaming data from the robots to the cloud, and as a bonus, we'll also cover how to save up to 10 times the cost on the clouds compared to other solutions like Timescale or InfluxDB. So in this video, we'll cover everything you need to get started with a clean recording pipelines for your robots. If you are new to the channel, I'm Anthony, co-founder at ReductStore, a high-performance storage and streaming solution for robotics and industrial IoT that we'll be using in this video. So that being said, let's get started. So this is what we want to set up. On one side, we have a device which is on the robot, can be a Raspberry Pi. In my case, I will use a Lenovo on my local network. And on the other side, we have another central storage where we run ReductStore and we want to get the data from the robots. The good thing about this architecture is that it will work the same if you have one robot or 100 robots. So if you have multiple robots, each robot will locally store data on a local ReductStore instance, and then all the robots will stream, push data to the central storage. So for this example, we'll also set up a few nodes. So we have topics we can record. We will use a USB camera, and from the raw images, we will use a tiny YOLO model, which will subscribe to the images and publish what it detects in each image. And then all those topics will be recorded with a recorder node, which will pack everything in separate MCAP files and store those files in ReductStore. And then we'll set up a replication task to stream data from the local ReductStore instance to the central storage. So first, I will launch this central storage on my laptop, but it could also be on a virtual machine or in the cloud. And to do that, I will head over the documentation. In the downloads section under reduct.store, you can find different ways to launch ReductStore. It can be with Docker, Snap, binary, and I will be using Docker, so with this commands, and this is pretty much it to get the server running. And you also have a web console which is running at ports reachable on ports 8383. And so ReductStore has a flat hierarchy, so it's organized into buckets. I will create a bucket called P robots. And each bucket can have different entries. And in one entry, you have records that are organized by timestamp, and so indexed by timestamp. And each record has a binary payload, and it's associated with labels, which are key value pairs that you can use for filtering and also replicating your data selectively, that we'll see later in this video. So for the buckets, I also want to make sure that I don't run out of space or I don't use too much space on my laptop. So I will set a limit at 10 gigabytes. So it's a FIFO quota, first in, first out. It means that if you have more than 10 gigabytes, which is used in the bucket, it will start removing all the files to make sure you don't go over this 10 gigabytes limits. And you can also provision the bucket with environment variable. For that, you can find in the documentation configuration different environment variables to set. For the buckets, you need to first set an ID, and then for each bucket, you can set a name for quota types and the size of the quota. Also, use token authentication if you want to organize different buckets and have different access depending on your applications. So next step would be to go over the robots. So it can be a Raspberry Pi. I will use a Lenovo on my local network and set up a local a ReductStore instance on this remote device. So first I will SSH into the device. So I have a Lenovo set up on my local network. And this time I will be using snap to launch ReductStore. So sudo snap install reductStore. That will fetch ReductStore and launch it. So that's it. You can follow the log as well with snap log. With the F flag to follow. And so same as with Docker, the web console is available at port 8383. In that case, it is available at this IP address, in my case, because this is the IP address of the Lenovo on my local network. And if I refresh, I can see the remote device, the web console of ReductStore. And same as previously, we will create a probots bucket, and this time we'll set up 5 gigabytes FIFO quota for the example to see how it works and how it handles incoming data. So here we go, and the next step would be to get some topics on the device that we can store with the recorder node. So first we want to collect images from the USB cameras with a node called V4L2 camera, and to find the command lines and the code we'll be using for all those ROS2 nodes, I linked the tutorial in the description, and we'll be using these commands to run the camera node, and with a few ROS arguments to set the image size and video device that we'll be using. So here we go, and then you should be able to see a new topic called image row, and this will publish images from your USB camera that have on this remote device. And next we want to subscribe to those images and infer detect objects from images with a tiny YOLO model with ONNX runtime. The code is available on the tutorial. So the first step is to install all the dependencies. So ONNX runtime that will run the model and OpenCV for Python. Then you can find the model on Ultralytics repository on GitHub, and you will need to first install all the requirements packages, that includes PyTorch, and then you can export the weight of the model with ONNX. And ONNX doesn't need PyTorch, and it's a great runtime to run AI models on edge devices. And then you need to get your ONNX file that you can add to your ROS2 workspace directory, and you can also create a package which will subscribe to images, to raw images, and detect objects in the images with the YOLO model. And so this is the code for it. You use you create a runtime session with ONNX using CPU, only in that case, and then you subscribe to the image row topic, and then for each image you need to change the formats so it's compatible with the inputs of the model. You infer the model, and then you look for all the detections, and it outputs what it detects, a class ID with a confidence score. The class IDs are objects that it detects in the picture. And in this example, I placed a cup in front of the camera, so it should detect class ID number 41. And then don't forget to add the entry points in your setup file. And you should be able to build the YOLO detector on your ROS2 workspace directory, source it, and then run. So we will run it for this example, and it should be able to detect the cup with every time different confidence score, right? But at least it works. It detects the cup I place in front of the camera. So now, again, if you look at the topic list, we can now see the object detected, image row, camera info confidence score, and also ROS out, so the ROS logs that we also want to store in our system. So now we want to subscribe to all those topics and store them first in MCAP file, so self-contained file, and split them by time or size. Use chunk level compression to reduce the file size, and then store that file in ReductStore. So for the recorded node, we will use ReductStore agents, which is available on ReductStore GitHub repository, that you need to clone on your ROS2 workspace and build. And also make sure to install a few dependencies like MCAP that we'll be using from Foxglove, and MCAP ROS2 supports, and as well as ReductStore SDK, which is called reduct.by. And once everything is installed, you only need to create a config file where you can define different pipelines and the storage where you want to store the data. So in this config file, you define the storage, so the URL where the ReductStore instance where you want to store the data, the buckets where you want to store the data, and then different pipelines. So in this example, we have one pipeline, and each pipeline is equal to one entry into ReductStore, but you can also have several pipelines, like it could be separated by camera stream, LiDAR scans, and then lightweight telemetry on another pipeline, for example. Here we have camera stream. We want to store image row, topic, the object detected, confidence score, as well as the logs, which is good practice to always keep in each MCAP file. And then we specify the split. So max duration 60 seconds, can be more or less, and basically every 60 seconds or every minute it will create a new MCAP file with all those topics inside and store that in ReductStore. Or if it reaches more than a megabyte, or it can be 500 megabytes and so on, it will split the file. The compression algorithm to define, you have either LZ4 or ZSTD, which is chunk level compression, so it doesn't compress the whole file, which is best practice in that case. And then also the file name can be defined as timestamp or incremental. Timestamp mean the file name will be the first timestamp of the topic it records in the file. So if we have a look at the ROS2 workspace, I should have a config file available. I will store all those topics, included ROS out, and I want to update one file into ReductStore every 10 seconds or every 500 megabytes. So if I run the ReductStore agents, it should subscribe to the topics and start recording MCAP files into ReductStore. So if we go back into our instance, so this is on my laptop. I want to find, so here we go. We have the camera stream entry that was created on the Lenovo, and then we have new files that are being created every 10 seconds. And it has a FIFO quota, so it should not reach more than 5 gigabytes. And so here it is for now less than a gigabyte, but as it increases, we will see that it will limit the amount of space it uses and start removing older files to make sure it doesn't reach more than 5 gigabytes. And next, we will now set up a replication task to stream data from the robot to the central storage. So to set up a replication task, I will go back on this instance and on the Lenovo. As you can see, it reaches now 5 gigabytes, and so it stops, so it records new files, but it also removes all the ones automatically. So for the replication task, I will be using the web console, but it's also possible to use environment variable. And so I will add a replication called to laptop, source bucket, PyRobots, destination bucket, same, I called it the same way. For the host, you need to know the IP address of your destination instance. In my case, it is my laptop on the local network. And if I remember correctly, it's ending by 54. So I will just add the IP address, 178.54 port 8383. And I don't use token authentication. And you can also specify when condition, and there is documentation about it. Basically, you could say, I want to store every n record, like every 2 files, I want to replicate to central storage. Or if you have specified labels with your records, you could also filter those records selectively with the when condition. For example, here you set the label name, and you can set condition like greater than or equal and so on. So here I create a replication task, and it should start replicating new files that are coming in into my laptop. So here we have one pending record. Okay, done. And if I go over my laptop, so it's on my local network, port 8383, I have now one new entry with the camera stream, and the data are coming in, as we can see. So they are coming as they are being created. And on my laptop, I also have a FIFO quota, but this time of 10 gigabytes. So here we go. You already have full recording pipeline from the robots to a central storage, and you could have multiple robots that are streaming data in that way to the central storage. So next step is how can we save costs if we have a central storage in the cloud. To do that, I will head over the documentation. So we have a section called Cloud, and it will work the same on Google Cloud Storage, Azure, or AWS. The principle is the same. In this example, I will show you for Azure. So the idea is that you run the database instance on a virtual machine. And then this is the same if you have a time series database like InfluxDB or Timescale. And it uses disk on the virtual machine. And this costs a lot, especially if you store data like images or LiDAR scans. You really don't want to do that because it will just cost a lot of money in cloud infrastructure. So the trick is that you can use blob storage, which is quite cheap and appropriate for that type of data. And to connect a local folder with the blob storage, you will use a Fuse driver. So Azure has a Fuse driver, same on AWS or Google Cloud Storage. And this is very practical because then you can have all your data in the blob storage. And in the blob storage, you can set up cold data, hot data, and having backup. So you can use this technology, which is well known and to store your data. And this is an easy trick to save quite a lot on cloud infrastructure. So I hope you enjoyed, and see you in the next one.